All right, there we go. Okay, everybody, let's get started. Happy Halloween, everybody. Although we celebrated, at least in the building, on Friday, so I know that's a little, I guess, different. All right, so just a heads up on housekeeping. So the attendance grades are up to date. I do know that my TAs are still a little behind on getting through the homeworks. I checked yesterday, and they're still working on completing homeworks 5.1 to 5.3, so I know they've got a little bit of catching up to do there. Homework 5.4 is due today, and then homework 5.5 is assigned today. But really, I guess what's the star of the show is I've given everybody back their exam 2. I posted to Microsoft Teams a short little video where I went through the statistics for the exam. I'll say that I think that in general the class did very well. And if this gives you a little bit of a sigh of relief, this exam has 4 exams, and of those exams, I believe that the most difficult one is exam 2. And that even accounts for exam 4 being comprehensive. In fact, I would argue exam 4 is, I think it's a dead heat between exam 3 and exam 4 being the easiest exams. Because at least exam 3 is incredibly prescriptive. And with exam 4, it is comprehensive, but I'm not asking you the most difficult questions from each unit. I don't want to say it's easy, but it's fairly fundamental. So another thing I think is worth mentioning, we are in lecture 30, which means we are actually ending the Engineering 213. Today, we are going to have our last lecture on centroids, which is a little bit of a misnomer because we're not actually discussing centroids, we're discussing moments of inertia, but it's a follow-on topic from centroid computations. It's another section property value. And then we really only have 2 other topics in the class. The first is structural analysis, and that's not to say that we're just going to spend the rest of the class doing civil engineering stuff, but it's really about, in general, taking our principles of statics and looking at the internal forces in systems as opposed to the external ones. And that has applications in every field of engineering. I use the term analysis of structures because that's what the textbook uses, but it really applies to every discipline. And then our final topic in the course is the subject of friction. And with that basically ends Engineering 213. So hopefully you see that there is a light at the end of the tunnel. And December is not that far away, okay? So with that, let's go ahead and jump right in to the wonderful world of moments of inertia. So what I want to do is make sure that we recall the general concept of computing a moment of area. And a moment of area is basically just an integral of not just dA, but dA multiplied by some power of x. We already had a homework assignment, homework 5.1, where I had you perform that direct integration to derive the section properties for a triangle. I'm not going to make you do another integral-based assignment for moments of inertia, because if you can do these 2, then it's literally just throwing another x term in there and you get it. And really the point of that assignment is I wanted you to understand that if there were these references that you could use to look up moments of inertia for triangles or semicircles or centroids for moments of inertia, or centroids, I should say, for semicircles or triangles, that you understood where they came from. But what I want to do now is I want to look at actually computing moments of inertia of composite shapes using the algorithm that I believe would be most useful and beneficial to you as an engineer, and that is through the use of the Parallel-Axis Theorem. And so the Parallel-Axis Theorem is really going to be sort of the star of the show today. Now, with these, I can derive the moments of inertia of really basic shapes like triangles and semicircles. I can develop a neat little table of lookup formulas, if you will, that are useful to me as an engineer. I can do the same thing for moments of inertia. So to give you kind of an idea, if I wanted to compute the moment of inertia, let's say about the x-axis, okay? And notice I've got here my rectangle here. I've got my coordinate system, but notice where I've placed my coordinate system. Notice that this is the x-axis and this is the y-axis. But what is that point right there in respect to the rectangle? Where have I placed the origin? At the centroid, okay? So what I am computing is a moment of inertia with respect to the centroid. In fact, centroidal moments of inertia are among the most useful to us as engineers. And all I'll say about that is an incredibly standard place about which to compute the moment of inertia, but the main reason for it has to do with deformable bodies, has to do with deformations. Largely, what you will find is that flexural bending theory and what have you is a function of the moment of inertia being referenced from the centroid. The idea is that if I take an element and I bend it, okay, if I take an element and I bend it, let's say above the neutral axis, the element is experiencing compression. Below it, it's experiencing tension. But at the neutral axis, at the centroid, it's experiencing no deformation. Hence why we reference a lot of moments of inertia with respect to the centroid. Now, if we go through and evaluate this, the evaluation of this is pretty simple. Okay, we compute the area of some dA, some differential area of the region. In this case, it's b dy. Okay, so how do I get that? It's just the width of the rectangle times the thickness, and then I'm just integrating that. I'm just summing those up. But instead of just integrating dA, I'm integrating y squared dA. So I plug in my term for dA, y squared. I'm integrating. Look at my limits of integration. I'm integrating from the bottom of the rectangle to the top of the rectangle. If the rectangle is h tall, then I'm going from negative half the height to positive half the height. Past that, it just becomes alphabet soup. You know, just treat the y as the integral. So the integral of y squared is y cubed over 3, evaluated from negative h over 2 to h over 2. Plug and chug, do your algebra, and I get this, bh cubed over 12. The moment of inertia of a rectangle being bh cubed over 12 is among the most fundamental formulas that we use as engineers. It's one of those things that kind of goes up the path of importance to be one that you might want to memorize. You probably don't need to memorize it for this course, but for you civil engineers that decide to take courses in reinforced concrete design or structural steel design, or you mechanical engineers when you probably take machine element design and what have you, or just engineering 216 or BME 302, you're going to see this formula pop up quite a bit. Okay, and we're going to use it today. But this is another one of those reference formulas like you'll find in the back of the textbook. So like, for example, if I have, let's say, a rectangle, here's the moment of inertia with respect to the x-axis and the y-axis, but here's the moment of inertia with respect to the centroid, okay? And so the one thing I will say is make sure that when you're using these guys, you pay real close attention to what coordinate system that you're utilizing. So for example, you will see here, with the rectangle, I have a general purpose coordinate system measured from the end, and then I have a coordinate system as well measured from the centroid. And these moments of inertia here with the bars over them, those are the ones that are in reference with respect to the centroid. So just make sure you're being very careful with the usage, with what formula that you're using. And don't worry, we're going to have an example here where we get some practice doing this. So don't think you're going to fly blind into this process. With me so far? Okay, now what I'm going to show you is the algorithm that we're going to use to compute the moment of inertia of a composite shape. So if we talk about centroids, if you remember, yeah, we had an introduction to centroids where we had to break out some integration and derive some formulas. But ultimately, if we really wanted to roll up our sleeves and actually compute the centroid of an engineering part, we didn't use the integration. We took the part and we split it up into a series of simple shapes. So if you have some region, let's split it up into some rectangles, some triangles, some circles, some semicircles, and handle each of those parts one at a time. And so, for example, if I wanted to compute y bar, it would just be the sum of y times a divided by the sum of a. There was an algorithm that went along with that. So split it up into simple shapes. For each shape, write the area, write the y coordinate of the centroid, and then just sum up YA, sum up A, divide, there's your centroid. That's the algorithm, right? There's a similar algorithm for moments of inertia, although it's a tad more involved, okay? Oftentimes in engineering, we want to, as I mentioned, we want to express the moment of inertia with respect to the centroid, okay? I stole a little bit of my own thunder here because knowing the moment of inertia with respect to the centroid is incredibly important for stresses, particularly in elements that are bent, things like in beams and frames. Now, the way that we handle that, especially if we have some of these references where we're breaking things down into simple shapes, is we shift the axis. And what I mean by that is instead of integrating, let's say, y squared, I'm going to integrate not y squared, but y sum plus some shift, okay? And so what will happen is if I take this expression, and let's say, let's go from here to here, so how do I get from here to here? I'm just foiling, right? So y squared, and if I have this times this, I'm going to have y dy and y dy, so two of those, plus the last term, dy squared. Then what I'm going to do is I'm going to take this and break it down into a bunch of smaller integrals and take a look at each of these one at a time. So this first integral, that's just the original moment of inertia. This middle integral here, I'm going to get back to, but this one here is just the area times that shift squared. So what's going on with this? Well, let's look at what we have here. We have 2 dy times the integral of that. But have we seen that integral before? Yeah, we've seen it before. We saw it in reference to the centroid, right? So if we're placing our coordinate system at the centroid, that means y bar is 0, so that means this integral is going to be 0, so we can sort of ignore that. So what I can do is, if I have the original moment of inertia and I want to shift it, I can shift it by taking that and adding this term AD squared. So if I sum up I plus AD squared for a given region, that will give me the moment of inertia with respect to my chosen coordinate system. And the vast majority of problems that we're going to look at, that chosen coordinate system is the centroid of the composite shape. So we're going to have an algorithm that we're going to use to compute the moment of inertia of a composite shape using this, the Parallel-Axis Theorem. And so what it's going to require us to do is compute the centroidal moment of inertia of each individual shape, the area of each individual shape, and these little d distances. And these little d distances are really easy to compute if you've already taken some time and computed the centroid. And I think the easiest way to understand this algorithm is to just do one, okay? So this is going to be what we look at today. We're going to compute the moment of inertia with respect to the centroid of this region, of this shape, okay? And it's involved enough that I think it'll give us some understanding of how to compute moment of inertias, but it's simple enough that I think that we can all utilize pretty much the same approach and get the same answer. So the other thing I will say is we're only computing the moment of inertia with respect to the x-axis, not the y-axis. So really all I'm interested in is figuring out where I place the x-axis and where I start defining these distances. Okay, so we're going to take our time with this. Don't worry. All right, so here's the problem. Okay. All right. Here we go. Okay. So the first thing I'm going to do is I'm going to take this region and I'm going to split it up into some very simple shapes. So do this, and we'll do this. Okay. So, excuse me. So we'll call So we're going to split this up into 4 regions. Let's keep it simple. Let's call shape 1 this rectangle. Let's call shape 2 this triangle. Let's call this the semicircle. Let's call that the circular hole. So one of the things I'll go ahead and do is that. And so all I'm doing is I'm just making a point that the rectangle, the triangle, and the semicircle all have positive areas, but the circular hole is going to have a negative area because we're removing that from the section. And so I think you'll see how we'll handle that, but you know, should be pretty straightforward. Okay. Okay. Now, in order to in order to compute the moment of inertia, the first thing that we're going to need to do is compute the location of the centroid. Okay? In other words, ultimately what I want to find is the moment of inertia with respect to the centroidal axis, but I don't even know where the centroidal axis even is. Okay? So what we'll do is we'll say, okay, I'll tell you what. I'm going to define a line here at the bottom. And so if you want, we can call this, I usually call it something like a reference datum. But ultimately what we're interested in is wherever the centroid is. Now let's just make up a point. Let's say the centroid is, I don't know, like right there. I just made that up. I don't know if that's the right place or not. But really what I'm interested in is the centroid with respect to this shape, or to this axis, okay? And what we tend to call that is NA, or the neutral axis. So if you want some terminology there, wherever the centroid is, the axes going through that centroid are the neutral axis, okay? So the first thing I'm going to need to do is figure out Y bar. I'm going to need to figure that out, okay? So I'm going to handle each shape one at a time. And let's start off with the simplest shape. Let's start off with this rectangle. Okay? Now, here's this rectangle, okay? And so the first thing I'm going to do is I'm going to look at this. Let's see, okay, I got a lot of terms with respect to B and H, okay? So for this rectangle, would you agree Would you agree with that? B is 10 inches and H is 8 inches. I think it's pretty simple. So I'm going to compute a few different quantities. Okay. The first thing I'm going to compute is the area, which I think I can do that one in my head. Okay. I'm going to compute y. Now, if I was computing the centroid, I could compute x and y, but I'm really only interested in y for this problem, since I'm only talking about the moment of inertia with respect to that horizontal axis. So all I care about is y. And now, notice how there isn't explicitly a formula given, and sometimes that might be the case. But let's just be honest with each other. How far is it from the bottom to the centroid of that rectangle? Halfway up, height over 2. Okay. Now, one thing I did sort of gloss over, some of you might go, wait a minute, hold on, Dr. Mike, how did you get that this was 8 inches tall? Well, I did it by looking at the semicircle. This semicircle has a radius of 4 inches. So if this semicircle has a radius of 4 inches, what's its diameter? 8 inches. So I did sort of gloss over that a little bit, my apologies. But yeah, if this semicircle has a radius of 4, then that's 4. So that and that is 8 inches. Okay. Now finally, and this is where things get new, is I'm going to have to compute this new term here called a moment of inertia. Now, what I'm interested in is the centroidal moment of inertia for this rectangle. Okay? So I got to be careful as to which one that I use. I'm not going to use the IX and the IY because that's with respect to this right here. I want the moment of inertia with respect to that point. So that's where you can see there's this X prime and Y prime, and so I'm going to use these. So I'm looking at this one right here. So I'm going to do, bless you, 1/12 BH cubed, which is the same thing that was in the previous slide. So this is 1/12. And then we have 10 inches, 8 inches, and that 8 inches is cubed. And so what do we get for that? You break out your Casio FX 115 ES Plus or similar scientific calculator. It's Monday morning. It's raining. Do we really have to break out our calculators? Yes. You're engineers. It should be the opposite. When do you not need to break down your calculators? What do we get for this? Anybody?
2,560.
2560. That's not what I got. Did you cube the 8, just the 8? And did you divide by 12?
Oh, I didn't. I divided by 2 instead of 12.
There we go. Now, the units for this are a little weird, okay? The units are inches to the 4th. I know we haven't entered the 4th dimension. It's just sort of an area times a moment arm squared. So yeah. I know those units are a little strange, but okay. So that's all we need for the rectangle, and if just for posterity, I'll just say here's our rectangle, 10 inches, 8 inches. Okay. Now, so now we have our triangle, and for our triangle, I'll draw sort of our triangle over here. So what we have is a triangle that looks something like this, and this is 8 inches, and this is 8 inches, right? Because that's the height, and then this width is given right here is 8 inches. So for this triangle, we know that Okay. Now, likewise, we're going to need an area, we're going to need a y, and we're going to need an IXC. So let's start off with the area. How do I compute the area of this triangle? There we go, BH over 2. I think I could do that one in my head. 8 times 8 is 64, divided by 2 is 32 square inches. Now, y? Okay, now let's be clear, okay? This is just a centroid problem. How far is it, I'm asking everybody here, how far is it from our reference to the centroid of this triangular region? If I wanted to find the centroid of just this triangular region right here, how far is it from my reference to the centroid of that? How do I do that? H over 3. That 8 inches over 3. It's 1/3 up, right? Same thing as our reference over here. Now notice that wasn't given here in this guide, but again, there's a centroid guide in the manual, and plus the B over 3, H over 3 value is one that I kind of think you ought to remember. So that one's going to be, I think I might be able to do that one in my head, 2 and change, like 2.67. All right. But again, so IXC, okay? Again, you got to be careful. I want the centroidal moment of inertia. I do not want the moment of inertia with respect to this axis here down below. Make sure you're paying attention to the schematic. I have the x-axis, but then the centroidal x-axis. This line is going through the centroid. The one that references the centroid has a denominator of 36, not a denominator of 12. So again, make sure you're being very careful as to what you use here. BH cubed over 36. Now that one I'm not that good. I need some help on that one. What do you get when you break out the Casio FX 115 ES Plus or similar scientific calculator? 113.77. 0.77. Do I have a second on that? And again, inches to the fourth. Again, I know those units are weird. All right. Next comes our semicircle. All right. So our semicircle looks something like this. Hold on. I'm going to scroll a little bit. My apologies, but I got to be a little neater. And so we know that our radius for our semicircle is 4 inches. Okay? So what do we need? We need the area. Now, how do I compute the area of a semicircle? Somebody help me out. If I know, let's be clear, if I know that the radius is 4 inches, how do I compute the area?
Pi r squared divided by 2.
There we go. All right. So that's 16 over 2 times 8, or 16 over 2 is 8, so 8 pi. Was that about 24, 25 something? There we go. Now what about y? How far is it from the bottom to the middle of this? Well, let's be clear. The centroid of this region is probably, let me move my 4 inches down a little bit. The centroid's about like that. But how far is it from here to here? What's that? Is it 5? 4. Yeah, it's just the radius. Okay. Now as for Ix, okay, let's see. We got kind of lucky with Ix, okay, and I'll tell you why. For semicircles, the moment of inertia actually changes or doesn't change dependent upon which direction that you flip it. But that's not always the case. Okay, I'm going to scroll up a little bit because I kind of want to make a point about something. Okay, let's take a look at this rectangle. Okay, so the moment of inertia of a rectangle with respect to its centroidal x-axis is bh cubed over 12. But if I take that rectangle and I turn it 90 degrees, the moment of inertia doesn't become bh cubed over 12. It's b cubed h over 12. You flip what you're cubing. So we're kind of fortunate with semicircles here, but all I'll say is you kind of got to make sure that you're dotting your I's and crossing your T's on your bookkeeping. Oh, that's 4. So I need some help on that one. I'm not that good. Man, kind of sloppy. And finally, we do have a circular region. Now, what's the radius of that hole? We're told it's a 3-inch diameter hole, so the radius is half that. So the area is pi r squared What is that?
7.07.
All right. Does anybody see something maybe I'm glossing over? negative, okay? So I'm just going to put a negative term right there so that when we list that in our table that we're going to draw here in a little bit, that we're indicating that that's in fact negative, okay? Now the y we kind of have to reference from our diagram, all right? So help me out. What is y going to be for this hole? How far is it from the center of this hole to down here? 5 inches. The total height's 8 inches, and we come down 3, so it's 5 inches. Everybody see that? Okay, so all right. Scroll up here a little bit. And lastly, our moment of inertia is, and again with circles, it kind of doesn't matter what axis that you're looking at, so we kind of get some benefit there. So it's just pi over 4, r to the 4th, which kind of makes sense. I mean, you would think that a circle is going to be twice as stiff as a semicircle, and this is pi over 8, and that's pi over 4, so that kind of makes sense. Oh, that's not 8, that's 1.5. All right, so what do we get when we check this out? Have a second? Okay, and this term is also going to be negative, okay? Like with centroids, so let's be clear generally about what we're talking about. A moment of inertia is a reflection of how stiff an element is. So just as we can't count the area as positive because we're removing the area from the shape, we can't count the moment of inertia as positive either because that hole is not contributing to the stiffness of the shape because it's not there. We're removing it. Okay, with me so far? All right, so if you recall, remember how I said that with centroids, that was the hardest part, just getting the A's, the X's, and the Y's for each shape? With the parallel-axis theorem, same story, okay? Okay, so the parallel-axis theorem states that we sum up the following. We sum up these. And let me show you how that works. Okay? I'm going to draw a table. It's going to be pretty big. It's going to have like 7 columns in it. So I'm just telling you that now so that as you're preparing your notes, like Dr. Mike keeps adding columns to this table. What's going on? It's going to have like 7 columns, so just be aware of that. Okay. 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 The very first part of this table, in fact, like the first half of this, should be incredibly familiar. Okay? What we're going to do is we're going to compute the areas. So what were the areas? We had 80, we had 32, we had 25.13, and negative 7.07. Was that right? So when you sum those up, I'll do that for you. You get 130.06. All right. Next, we're going to write the y distances that we computed for 2.67, 4, 5. And then now we do the YAs. So 320, 85.5, 33. So I'm just going to go ahead and do this part for you because I would hope that this part's pretty simple. 100.53 and then negative 35.34 with you if you trail all the decimals and whatnot. Okay, and sum that up. And then when you chug this out, you get like 3.618 inches. Now, I want to stop for a sec. I know I blew through that kind of quickly, but we've already done that, right? That shouldn't be all that mysterious. Right? It's the same stuff we've been doing. Okay. So maybe what we'll do is we'll just sort of say, that part of the table is just locating the centroid, and that's no different than what we've done before. No different at all, okay? All right. With me so far? Okay. The rest of this algorithm is really easy, okay? So, first thing that we're going to do, let's list these out, okay? So what did we get? We got that. We got that. We got that. And then negative 3.97. Okay. Now let's take a moment and actually look at the parallel-axis theorem. This is the parallel-axis theorem. This is the method that we use to shift our axes such that we are computing the moment of inertia with respect to the centroid. Okay? Now what do we mean by shift the axis? Aren't we already referencing with respect to the centroid? Not really. Okay? It is true that these values here are centroidal moments of inertia, okay? But they are moments of inertia with respect to the centroid of each individual shape, okay? This is the moment of inertia with respect to the centroid of just that rectangle. This is the moment of inertia with respect to just that semicircle. I don't care about those individual shapes. I care about the whole thing, okay? So I want the moment of inertia with respect to the whole region. So how do I do that? I need to compute a D value for each one of these, but it's really easy. Okay, all I do is take the Y value for each shape and I subtract Y bar. Okay, that's it. Okay? And to give you kind of an understanding of what we're talking about here, let me scroll up a little bit to kind of explain why this works. Okay? All right. So what did we get for Y bar? 3.618. Is that what we got for Y bar? Okay. Now let me ask you this. How far is it from here to the center of the rectangle? From here to the center of the rectangle, how far is it? 4 inches? So the centroid of the rectangle is probably like right here. So what I'm interested in is shifting that value for the moment of inertia for the rectangle up that much. And how much is that? Well, it's 4 minus that, right? From here to the red cross is 4. From here to the green cross is that. So that is just the difference of the two. So if I go down here, is 4 minus 3.618? It's like, what is it? 0. We'll just call it 38. Is that fair? Now, here's another thing to make sure that you're paying attention. Did it matter what order I did that subtraction in? Like I did y minus y bar. What if I did y bar minus y? Would it matter? Why? You're shaking your head no. Because you're going to square it. It doesn't matter what direction that you subtract it in because you're going to square it. So you can kind of be pretty fast and loose with your direction here because you're going to square it anyways. It doesn't really matter. So this one I'm going to do 2.67 minus 3.618. This one I'm going to do 4 minus 3.618. Which I just did that one. This one I'm going to do 5 minus 3.618. This one I can do in my head. This one I might need to reference, and I get negative 0.95. All that negative means is that for these three, I go up. I have the shifting is sort of upwards, and for that triangle, the shift is downwards. It doesn't matter because I'm squaring it anyways. And so now what I'm going to do for each of these is compute that. Moment of inertia plus a d squared. So like for this first row, it's going to be that value plus that times this quantity squared. Somebody tell me what you get when you check that out. I'm just curious. That plus that times this quantity squared. .81? Is it .38 or point? Did you put .38 or .038?
I put .382.
.38 squared.
382 squared. Yes. Yeah, I can do without the 2.
No. You're only squaring the d. Here's what I'm getting at. I got 438.36. My value was a little. Is that what you got? Yeah, I would make sure you wrap your parentheses around the squaring because you're just squaring the 38, the .38. Bless you. Did anybody else get what I got? Okay, all right. Check your parentheses on yours.
It was a mistype.
All right, that's okay. That's all right. Now, for the remainders, I'll go ahead and do the remainders. So this next one is going to be like that plus that times that squared. And so when you check it out, you'll end up getting like 142.72. 104.21 and minus 17.48. And then all you do is you just sum these up and you end up getting something like 667.80. So therefore, you just get that. Now, I'll go ahead and tell you, just to be blunt, in the land of rigid body mechanics like statics, this value doesn't have a lot of strong implications. This really only matters when you start getting into deformable bodies, because in the land of deformation, that will tell you how stiff the element is with respect to deformation. So there's two things I want to say, and then I'll close it. Okay, what we computed was an x-axis moment of inertia. What if I wanted to compute a y-axis moment of inertia? So a y-axis moment of inertia I can handle two ways. The first way is to just invert my coordinate system, in other words, to reference everything with my distances this way instead of up and down. The other way is to literally just take the shape and turn it 90 degrees. Actually take it and turn it up like that. Either way will work, and it's just the same process over and over again. The other thing I'll say, and then I'll let you go, is that what we computed just now was an area moment of inertia. Next semester in the land of dynamics, there is a concept called a mass moment of inertia. And mass moments of inertia are important for understanding rotational kinematics and whatnot. That's a story for next semester. So you are going to kind of see some of this stuff in future courses. All right, I'm going to pull the QR code up again. If you have not grabbed your exam, please do so. Please, I appreciate it. That's all I got. I will see you all on Wednesday.